we're going to talk about exponential functions. An exponential function, which is f with a base of b, is defined by f of x equals b to the x, or we know that f of x is the same thing as y, so y equals b to the x, where b is a positive constant other than 1. b has to be greater than 0, and it can't equal 1. Because if b equals 1, 1 to any power is going to be 1. So it's not exponential. It's just going to be a flat line of 1. So for example, we have f of x equal 2 to the x. That's where our base is 2. G of x equals 10 to the x, where the base is 10. H of x equals 3 to the x plus 1, where the base is 3. And j of x equals 1/2 to the exponent of x minus 1. That is base equals 1/2. So each function has a constant base and a variable exponent. By contrast, the following functions are not exponential functions. This is f of x equal to x squared. Well, this is because the variable is the base and not the exponent. G to the x equals 1 to the x. Well, that's because the base is 1 and the base cannot be 1. Here we have h of x equals negative 1 to the x. Well, that won't work either because the base has to be positive, because otherwise the value will flip back from negative to positive. So it's not going to exponentially grow or decrease. And h of x equals x to the x, well, the variable is both the base and the exponent, so it's also not going to be an exponential function. All right, so here we have two graphs. This is going to be an exponential function where it is increasing, and this one is decreasing. So the increasing is where our exponent is going to be greater than 1. So we're going to be, or our base is greater than 1. So we're going up because we're going to have a whole number that increases as we square it or cube it or whatever. Here, if our base is less than 1, between 0 and 1, then we are looking at it increasing, because the smaller our value, or the bigger that the value in the base gets, between like 1/2 and 3/4, it will become, it'll keep decreasing and get smaller as it comes down this way. The base will actually, the result will actually get us a number that comes along here, so it'll get a little bit greater because it won't be in this negative side, but it will, as our x becomes positive, our y value is decreasing, which is where we have y equals b to the x. All right, some characteristics of exponential functions. The domain consists of all real numbers, so you're going to have negative infinity to infinity in both cases. The range also consists of all positive real numbers, so they're going to be from 0 to infinity in both cases. The graphs of all exponential functions in the form pass through this point of 0, 1, because f at 0, which is b to the 0, equals 1. Remember, b can't be equal to 0, but our exponent can. So it will always pass through there. So that's going to be your y-intercept. And there won't be any x-intercepts because it's never going to cross the x-axis. If b is greater than 1, the graph goes up to the right and is an increasing function. The greater the value of b, the steeper the increase. So as b is greater, the curve will either, as you get a bigger b, it will get steeper. Instead of being more gradual, it'll be a steeper curve. If our b is between 0 and 1, the graph goes down to the right and is a decreasing function. The smaller the value of b, the steeper the decrease, which is what I was trying to explain earlier. So the smaller your b, if you have a bigger b, it's going to be more curved a smaller b is going to be more steep. It is a one-to-one function and has an inverse that is a function. The graph approaches but does not touch the x-axis. The x-axis, or y equal to 0, is a horizontal asymptote. So here's a little bit bigger picture. You can see they both cross through the point of 0, 1. This shows you that we have a b between 0 and 1, and here our b is greater than 1. And there's our horizontal asymptote. The function f of x equals e to the x is the natural exponential function with base e. The value of e is between 2 and 3, since 2 squared is 4, and 3 squared is 9, and e squared is 7.389. So that puts the value of e somewhere between 2 and 3. All right, so let's look at our first example. So we have y equals 2 to the x and y equals 6 to the x. And we need to figure out which graph on here is our the graphs we are looking for. All right, so this is 2.5 in the class, and we are looking at example 1. We have y equals 2 to the x and y equals 6 to the x. Now, some of the things we just talked about, they both have a base that's greater than 1. So we know that both of their graphs are going to increase. We know that because the b is greater than 1. Now, on our chart here, we have a couple of graphs that increase. So which one is it going to be? Well, we can look at the fact that the base of 6 is larger, because the larger our b, the steeper the curve is going to be. So because of that, we can see, if we're looking at h and k, we can see that k is going to be the steeper graph because the 6 is larger, and h will be the graph with the 2 to the x. Now, how do we know for sure? We can always do a t-chart. So we can do a chart that looks like a T with x and y, and we can pick some values. So if I pick 1, 2 to the first power will get me 2. If I pick 2, 2 to the second power, so this would be 2 to the 1 equals 2. 2 squared equals 4. So that gives me an idea there. Let's go do the same thing over here. We have our x and we have our y. Let's pick the same numbers. So let's pick our 1. So 6 to the 1 will get us 6. And 6 to the 2 will get us 36. So you can see how much quicker y equals 6 to the x is going to increase. It will have a steeper graph. So let's look at a couple more. I'm not sure why they're not on our handout. I'll get them added there. So what if we also have y equals 0.2 to the x and y equals 1/3 x? Now I'm going to put those in parentheses just so that you can see the whole thing is being raised to the x. Now these are less than 1 for our b, so we know that our graph is going to look like this. It's going to curve. But we also talked about that it's kind of hard to compare these. You've got to think about it. So 1/3 is going to be the same as 0.33. So I'm just going to put that in parentheses. So this would be like 0.33. We can see that 0.2 is smaller than 0.33. And if you recall, it says the smaller the value of b, the steeper the decrease. So this one's going to be smaller, so it's going to have a steeper decrease. Now again, we can make a t-chart. And we can use 1, and let's use 2. So if I plug in 1, I get 0.2 to the first power, which will be 0.2. If I plug in 2, I get 0.2 squared, which will get us 0.04. And then if we plug in 1 here, we get 0.33. We should just use the 1/3. Let's do that. So if we have 1/3 to the 1, we're going to get 1/3. If we have 1/3 squared, we will get 1/9, which is the same thing as 0.111, just so we can kind of compare across. Now, this is a little bit harder maybe to see what's going on with the graph, so let's pick another number on this one. So let's pick -2, so we can see what's happening on the other side of the graph. When I take 0.2 to the -2, I'm going to get 25. When I take 1/3 to the -2, I am going to get 9. Now I can see that this is a much steeper because it goes from 25 way down versus 9. So let's look at our graph. We have 4 graphs on here. So we know that H and K are going to be for these 2 graphs up here. So what we find, because we know that y equals 6x will be a steeper curve, this one is going to be graph K. Graph H will go to the y equals 2x. On this one, to the 0.2, we know that's going to be the steeper graph, so it's going to be graph G versus this graph will be graph F. So here we're just kind of starting to understand and learn what is happening with our exponential functions depending on what our base is and then what we raise it to. All right, let's go look at example 2. So for example 2, we are going to graph the function of y equals 3 to the x on the interval of -3 to 3. Now I have a couple of pictures on your handout so you can get a good picture versus what you're going to see me draw, because we do the best we can. So what I'm going to do, I've got y equals 3 to the x, and it's on the interval of -3 to 3. So first thing we need to understand, this is not going to be a graph that goes on and on. We're going to stop at -3 and 3 between that interval for our x values. So let us make a t-chart for this one. So we're going to do several points. I'm going to do -3, 1, 0, 1, and 3, because I want to get a good graph as I draw it. When I raise 3 to the -3, I'm going to get 0.037. When I raise 3 to the -1, I'm going to get 0.333. 3 to the 0, we've already talked about anything to the 0 power is 1. And then 3 to the first power will be 3, and 3 to the third power will be 27. All right, so let's go graph. We may not plot every point exactly. We'll see how it goes. We're going to have to do some quick climbing, so I'm going to probably do increments of 5. We know we're not going below the x-axis because there will be no x-intercepts with our exponential functions. So we're going to do about, we're going to go through the 1. So we'll count this as 1. And then I'm going to kind of jump a little bit here. So let's call this 5, 10, 15, 20, 25, and 30. Because I want to show you it's going to go through the 1. Now our bottom graphs, they can just be at 1 increments. All right, so at negative 3, we are at, let's grab another color, we are at 0.03. So we're going to be really close, but not on the x-axis. At negative 1, we're at about a third of the way up. At 0 for x, we're at 1 for y. And then at 1, we're going to be at about 3, about right there. And at 3, we're going to be up here to 27. Now this is not a great graph because I have jumped once I got going. Now notice I stop at both points. I'm not drawing arrows because it's on the interval of negative 3 to 3. All right, our next example is not on our handout. We are going to describe verbally the transformations that can be used to obtain our graph. So we're going to, in words, describe the transformation. So for part A, we have g of x equal to 5 to the x minus 7. So we've done things like this before. We've done transformation of graphs, so it's going to be similar to what we've learned before. So in the parentheses, or the exponent up here, we are looking at right or left. And it's going to be very similar to what we did before. Because we see the negative, we usually think, oh, we're going to the left. But actually, it will go to the right. So this will shift. And this is g of x going from f of x equal to 5 to the x. So we're comparing the two. What's going to happen to the g function versus where the f function is? This is going to go right 7 units. Okay. Now, if we look at b, if we have g of x equal to e to the x plus 4 versus our f of x equals e to the x. Notice that the minus 7 was in the exponent before. Now it's sitting level with the e. So that tells us it's going to go either up or down. And because it's positive, it means we're going to go up. So we're going to go up 4 units. So if you recall, doing our exponential or our transformations earlier in the semester, these will be very similar as to how they look. All right, we are going to go look at our handout here for just a second. So we're looking at solving exponential equations by expressing each side as the power of the same base. So if we have b to the m equals b to the n, then the m and the n need to be equal to each other. If they have the same base, then the exponents have to be equal to each other or it's not a true statement. So we're going to rewrite the equation in the form that looks like b to the m equals b to the n, and then we'll set those exponents of m and n equal to each other, and we'll solve for the variable. So this is example 4. So we're just going to solve the equation. Oops. We're actually solving it for x. So if we have 5 to the 8 minus 7x equals 5 to the 4x minus 2, what we're stating here is if 5 is raised to the different powers, but they're set equal to each other, those powers have to have the same value. Because if we have 5 squared, it has to equal 5 squared. It cannot equal 5 cubed because it would be a different answer. So what we're going to do is take our exponents of 8 minus 7x and set it equal to 4x minus 2. Now we can only do this if we have the same base. So I got to decide which way am I moving my x's. I like to keep them positive. So I'm going to move this 7x over and get 8 equals 11x minus 2. I'm going to add 2 to the other side and get 10 equal to 11x. Divide both sides by 11 and we get x equal to 10 over 11. Okay, let's go look at our next problem. On example 5, we are again going to solve for x. So if we have 5 to the negative 4x minus x squared equals 5 to the third. Again, we have the same base as 5, so this will be negative 4x minus x squared equal to the 3. So here, I need to put everything on one side because I have an x squared. So I'm going to add my 4x and my x squared to the other side. So I have 0 equal to x squared plus 4x plus 3. Now, this is a quadratic equation, so we need to either use our quadratic formula or factor this. I'm going to factor this and get x plus 1 times x plus 3. Now we'll take each part and set it equal to 0. And we'll solve for each x value. So we have two x values, but we always need to check for extraneous answers, which means sometimes we will get a solution that doesn't work. So we're going to check these into our function. So first I'm going to check x equals negative 3. Doesn't matter which one you check first. So I'm going to get 5 to the negative 4 times negative 3 minus negative 3 squared equals 5 to the third. So this will get me 5. Negative 4 times negative 3 will get us positive 12. Minus negative 3 is being squared. So that will get us minus 9 equals 5 to the third. 12 minus 9 is 3. And so that checks. We have 5 thirds equals 5 thirds. All right, now let's check x equals negative 1. So 5 to the negative 4 times negative 1 minus negative 1 squared equals 5 to the third. Negative 4 times negative 1 will get us 4, so 5 to the positive 4 minus negative 1 squared, again, is a positive 1. And then 4 minus 1 will get us 3. So both answers work in this case. So if you're working it and you're doing your homework and it tells you something's wrong, that both answers are not the case, then go check them to see. We won't check every answer, but do check and be sure. All right, we are looking at example 6. So for example 6, again, we're going to solve for x. And we're going to remember that e to the negative x, it says, cannot be equal to 0. Okay? So here is our function. We have x times e to the negative x plus 3e to the negative x equals 0. It can't be equal to 0 because if it is, our whole equation goes away. Because then that means we've got 0 plus 0. So what we're saying is it cannot be. Now, how do we solve this one? Well, when we look at it, we do have a common e to the negative x. So e to the negative x, if we factor it out, we're left with x plus 3 equal to 0. We'll take each part again and set it equal to 0. And x plus 3 equals 0. We'll solve this one to get x equal to negative 3. Now, this cannot be a solution because we were told each of the negative x cannot be 0. So this one is not a solution. But x equals -3 can be a solution. All right, let's go look at example 7. Again, we're going to solve for x. So we have e to the 5x minus 1 minus e equal to 0. Now remember that e by itself is just a constant term. Remember we talked about it somewhere between the value of 2 and 3. So we can't really factor it out this time because it doesn't have an exponent. And this has an exponent, so we can't really factor it out. What we can do, though, is add the e to the other side. So e to the 5x minus 1 equals e. Now, what does this e exponent look like? Well, it's a 1, e to the first power. Because it doesn't have 1, we can put 1 there. When I have e to this power equals e to that power, so that means I have 5x minus 1 has to be equal to 1, otherwise it's not a true statement. So I'm going to add the 1 over, get 5x equal to 2, divide by 5, and x will be equal to 2/5. All right, now we're going to go look at compound interest. Compound interest is interest computed on your original investment, as well as on any accumulated interest. The principal is going to be, which is P, is the sum of money invested. R is your rate in decimal form, not percent form. Make sure you always change it to a decimal. M, in this case, will be the number of compounding periods per year. And T is time, which is the length of investments. So if you've done college algebra or other algebra classes, a lot of times they have N as the number of compounding periods, but in the business math, especially in this book, they use M. So just be aware of what your letters are. So A equals P times 1 plus R over M raised to the MT. And sometimes they'll use R over M is the same thing as I. And then M times T is the same thing as N. So just be aware of, they might also have it in this format in your homework. So I have them both there so you understand. For continuous compounding, we're going to use A equals PE to the RT, also known as the PERT formula. That is the same as you've seen it before. Remember the number of compounding periods per year. If it's annually, that's something that happens once a year, like your birthday or holidays. Semi-annually, it happens twice a year. Quarterly, 4 times a year. That would be like 4 quarters in a dollar, 4 quarters in an hour. Monthly is 12. There's 12 months in a year. And weekly is 52. Do pay attention. Sometimes they round that to 50 in some homework problems. Alrighty. So our first problem that we're going to do with using our interest formulas is find the value of an investment of $20,000 for 12 years at an annual rate of 4.95% compounded continuously. Continuously uses the E, so that's going to be your PERT formula. All right, so let's go look at example 8. So we're looking at using A equals PE to the RT. Let's put what we know. There's a value of an investment of $20,000. The investment amount, or the amount that you deposit, is going to be the P, the principal. Our next letter that we get is R. We were told that it was a 4.95%. We need to change that to a decimal. So you can drop the decimal and divide by 100, or you can know that you're going to move the decimal 2 places to the left. So 0.0495. Do pay attention to this because I'll have a lot of students who put 0.4 and not 0.04. So do pay attention. It's got to move 2 places, so you've got a 0 fill in there. And then our t, we are told that it is for 12 years. T always has to be in the form of years, even if they give you months. We'll look at some problems on that. All right, so we've got A equals 20,000 e to the 0.0495 times 12. And all we're going to do is take our calculator and we're going to put it in. So 20,000, watch how many zeros you put in. That's where I get a lot of students making mistakes. The e to the x is in my green key right here. So I'm going to do second button to get the green, and I get e to the box. Mine gives a box for some students. If you have an old TI-83 and an old TI-84, you might get parentheses, so do watch out what's happening there. So I'm going to put in 0.0495 times my 12, and then if you have where it does parentheses, make sure you close the parentheses there. But I'm going to hit enter, and I'm going to get 36224 point. This says 376. We're going to use regular rounding rules. So 5 or greater after the 7 tells me to round up. If it's less than 5, we will stay at 7. Because I have a 6 after the 7, the 6 tells me the 7 will round up, so it'll be 38. So you need to watch that as well, because in your homework, if you put in 37, it's going to tell you it's wrong because you didn't round correctly. If you're going to put the dollar signs go at the front of the number. They never go at the back. And that would be your answer. All right, let's go look at example 9. So for example 9, suppose $6,300 is invested at 3.1% annual interest rate, compounded monthly. How much, now because it's compounded monthly, we know it's not going to be a continuously, so we're going to use the other formula. How much money will be in the account in 9 months and 10 years? All right, so we've got a couple of things going on here. First of all, our formula is going to be A equals P times 1 plus R over M raised to the MT. So for part A, let's kind of list what they have in common. Our P, we are told, is that the amount we invested was $6,300. The interest rate is the same, so our R is 3.1%, which will become 0.031. And our M, it says that it's going to be compounded monthly, so M is still going to be 12. The difference will be that A, part A, our T, will be 9 months. So if it's 9 months, I have to put it out of 12 months so that it's in a year form. So we're going to do 9 out of 12. Okay? All right. And then for part B, our T will be 10 years. So it will just be 10. Okay? All right. So let's go do part A. So for A, we're going to have our P, which is 6,300. Oh, that's a big space there. Sorry about that. Times 1 plus our R of 0.031 divided by our M of 12 raised to the 12 times 9 over 12. Now, this is like 12 over 1. So if we're putting this in the calculator, the 12s will cancel and we can just put in 9. So that would be the same thing as 6,300 times 1 plus 0.031 divided by 12 to the 9. If you don't like that reducing, then you can just still put it all in at the same. All right, so let's go put this in our calculator. So we have 6,300 times 1 plus .031, divide by 12, raise it to 9. Okay, so we get 6447.997. That 7 is 5 or more, because it's 7, so that'll make the 9 round to a 10. Well, that will make this round to a 10, so the round will go clear over to the 7. So 6447.997 is going to cause the rounding to be 6448.00. Okay, so just be aware, and we're just looking at that number right after the 9. All right, let's go do part B. So for B, we're going to have our 6,300, still 1 plus 0.031 divided by 12, raised to the 12, but instead of 9/12, we're going to use our T as 10. Now, if you want, you can put that in the calculator as 120 instead of 12 times 10. It doesn't matter. For some students who have the older calculators, it can make it a little bit easier, but you can put it in 12 times 10. All right, so let's put in our 6,300, parenthesis, 1 plus 0.031, divide by 12. If you notice, too, I'm not putting in a fraction in my calculator because it will follow the PEMDAS rules. And then I'm going to raise it on mine. I'm just going to put 12 times 10, or I could put in the 120. It does not matter. You'll get the same answer. All right, here we have 8586.145. That 5 is going to cause my 4 to round up. So we're going to get 8586.15. We're always going to go to 2 decimal places when we are talking about money.